From a flicker of Volta's first pile to the silent precision of today's solid-state cells, this documentary traces the entire history of stored energy, how chemistry, curiosity, and perseverance turned sparks into the heartbeat of modern civilization. Part 1. The Birth of Power. Electricity has always been there. Lightning in the sky, the crackle of static, the shock that jumps from your fingertip on a dry day. But for most of human history, it was a wild force, untamed, uncontrollable, a spectacle of nature rather than a tool of progress. That changed in the late 18th century, when curiosity began to collide with understanding. In candlelit workshops and quiet European studies, scientists experimented with glass rods, amber, silk, and metal plates, seeking to grasp this invisible energy that seemed to obey no rules. One man, Luigi Galvani, noticed something peculiar. When he touched a dissected frog's leg with two different metals, the leg twitched. He believed it was life itself, a kind of animal electricity flowing through living tissue. But another thinker, Alessandro Volta, disagreed. He saw not life, but chemistry, the metals themselves at war. In 1800, Volta stacked discs of zinc and copper, separated by cloth soaked in brine. As he built higher, a faint current emerged. It was steady, continuous, and entirely man-made. The voltaic pile was born, the first true battery. It didn't roar or spark. It simply flowed endlessly as long as the chemistry held. Each pair of discs produced about 3/4 of a volt. Stack enough of them, and the power added up, proof that electricity could be generated, stored, and harnessed. To visualize it, imagine a tall column of coins, each layer soaked in salt water. Inside every gap, invisible armies of atoms trade places, zinc surrendering electrons, copper accepting them, salt water carrying the charge. Connect a wire, and those electrons march outward, powering the first flickers of electric light. The voltaic pile transformed electricity from curiosity to instrument. It powered early experiments in magnetism and electroplating, opened the door to telegraphs, and gave humanity its first glimpse of controllable energy. For the first time, the world could summon electricity at will. But Volta's invention had problems. The brine dried out. Hydrogen gas bubbled at the copper surface, choking the reaction. The zinc corroded quickly. It was a marvel and a mess. Still, every revolution begins imperfectly. Volta had captured the concept. Now others would refine it. In the decades that followed, inventors across Europe sought stability, a current that wouldn't fade, a reaction that wouldn't eat itself alive. The race to improve the battery had begun. By 1836, John Frederick Daniel, a British chemist, found a better way. His design, the Daniel cell, used a copper pot filled with copper sulfate solution and a zinc rod dipped into acid. A porous barrier separated the two liquids, preventing them from mixing while letting ions slip through. It worked beautifully. The current was steady, predictable, and lasted for hours instead of minutes. Telegraph operators adopted it immediately. For the first time, words traveled across nations powered by chemistry alone. As zinc dissolved and copper plated out, electrons coursed through iron wires, tapping messages that spanned oceans. A pulse from London could reach Paris in seconds, each dot and dash carried by the quiet work of atoms. The Daniel cell was more than an invention. It was a foundation. It showed that electricity could be engineered, tuned like music rather than summoned like magic. But progress never rests. Even this elegant design had its limits. Once the chemicals were spent, it died. and the world, already accelerating, wanted more than one-time power. It wanted rechargeable life. By the middle of the 19th century, the world was charging ahead on steam and steel. Factories roared, locomotives thundered, and telegraph lines knit continents together. But every line, every light, every instrument still depended on single-use cells that died once their chemistry was spent. It was wasteful, costly, and limiting. Then, in 1859, a French physicist named Gaston Planté discovered a remarkable trick. He took two thin sheets of lead, rolled them into spirals, and submerged them in sulfuric acid. When he passed a current through the plates, a subtle transformation began. One sheet became coated with lead dioxide, dark, rough, and hungry for electrons. The other remained soft metallic lead. When he reversed the current, both plates slowly returned to their original state. For the first time, energy could be given back. The battery could breathe, charge, discharge, and live again. The lead-acid cell was born. Its reaction seemed almost alive. Lead plus acid produced lead sulfate and water during discharge. Feed it power, and the reaction reversed, rebuilding the plates and regenerating the acid. Each cell delivered about 2 volts. String 6 together, and you had 12 volts, strong enough to crank an engine or light a street. To imagine what happens inside, picture 2 metal sponges soaking in acid. As current flows out, one sponge gives up material while the other absorbs it, both slowly whitening with sulfate. During recharge, those deposits dissolve back into the liquid, the sponges darken, and the cycle begins anew. It was heavy, yes, lead always is, but it was reliable, and it could be reborn hundreds of times. Soon, telegraph stations, railroad signals, and even early automobiles relied on it. The lead-acid battery became the heartbeat of the industrial age. Decades later, in the early 1900s, 2 inventors sought to push it further. In Sweden, Waldemar Jungner experimented with nickel and cadmium. Across the Atlantic, Thomas Edison swapped cadmium for iron. Both men dreamed of batteries that could last for years without failing. Their creations, the NCED and Ni phase cells, replaced heavy acids with alkaline solutions. Instead of corroding, their metals performed a disciplined dance. Nickel plates absorbed oxygen, cadmium or iron gave it up, and electrons marched through the circuit in perfect time. They were sturdy enough for rail cars, miners' lamps, and submarines. Edison boasted that his design could be charged 1,000 times, and in truth, many did. Some nickel-iron cells built before World War I still work today. But progress brings trade-offs. Cadmium proved toxic, iron cells were bulky, and both produced lower energy than chemical fuels. As the 20th century gathered speed, industry sought batteries that were not just strong and safe, but portable. Small radios, flashlights, and the first experimental aircraft demanded power that could travel. Chemists responded with refined dry cells, zinc and manganese dioxide sealed in paste instead of liquid. No leaks, no slosh, and enough capacity to bring the electric age into every home. Children wound their toy trains. Soldiers carried torches through trenches. Farmers used wireless sets miles from the nearest wire. Electricity was no longer confined to cities or factories. It had become personal, a spark in every hand. Yet even as these dry cells spread across the world, another limitation loomed. They were disposable. And in a century soon to be defined by mobility and machines, disposability wasn't enough. The next leap would demand something lighter than lead, cleaner than nickel, and capable of holding far more energy in far less space. The world needed a metal so eager to give up electrons that it bordered on reckless. It needed lithium. Lithium, the lightest solid element on Earth, number 3 on the periodic table. A metal so reactive it bursts into flame if it touches water, yet so promising that scientists couldn't resist it. From the beginning, they knew its potential. Each atom of lithium carries a single, eager electron, bound so loosely that it's almost begging to escape. Harness that restlessness safely, and you unlock extraordinary energy. The dream of a lithium battery began in the mid-20th century. By the 1950s, engineers had already tried zinc, nickel, iron, and silver. Each chemistry had its strengths, but none could match the energy density that lithium's atomic weight promised. The first designs were primary lithium cells, single-use, non-rechargeable. They powered pacemakers, cameras, and military equipment where longevity mattered more than reusability. But researchers wanted more. They wanted a battery that could recharge like lead acid without the bulk and last for years. The challenge was stability. Lithium is highly reactive. It forms dendrites, tiny metallic spikes that grow like frost inside a cell and short it out. Early prototypes caught fire or failed catastrophically. Progress stalled, but curiosity didn't. Then, in the 1970s, a breakthrough. British scientist Stanley Whittingham discovered that certain layer materials, like titanium disulfide, could host lithium ions between their atomic sheets. Instead of pure lithium metal, the ions themselves could move in and out, leaving the structure intact. It was a revelation. Instead of a violent chemical reaction, the battery could act like a lithium shuttle system, ions moving back and forth quietly, predictably. In the 1980s, another mind refined it, John Goodenough. He replaced titanium disulfide with cobalt oxide, which provided higher voltage and more stability. Finally, in the mid-1980s, Akira Yoshino of Japan built a fully functional prototype using a carbon anode, graphite, to absorb and release lithium ions safely. In 1991, Sony brought it to market. The world's first commercial lithium-ion battery. The age of modern portable electronics had begun. To visualize what happens inside, imagine two hotels on opposite sides of a quiet river. One is the cathode, built of cobalt oxide, packed with lithium guests. The other is the anode, layers of graphite waiting with open rooms. Between them flows the electrolyte, the river that only ions can cross. When the device powers on, lithium guests check out of the cobalt hotel and cross the river as Li ions. Their luggage, the electrons, can't cross the river directly, so they take the long scenic route through your phone, your laptop, your car's motor, doing useful work along the way. At the anode, the ions and electrons reunite, ready for the next trip. When you plug in your charger, everything reverses. Electrons flow back, ions cross the river in the opposite direction, and the battery refills, a quiet dance of order restored. That shuttle system changed everything. For the first time, electricity became truly mobile, not tied to the wall, but carried effortlessly in your pocket. Laptops replaced notebooks. Cameras went digital. Tools went cordless. And eventually, vehicles began to shed the weight of gasoline for something cleaner, lighter, and smarter. Yet success revealed new weaknesses. Lithium-ion cells were powerful but volatile. Push them too hard, and their electrolytes, made of flammable organic solvents, could ignite. A puncture, a short, or a manufacturing flaw could trigger what engineers called thermal runaway. It was chemistry turning against itself. Over time, engineers tamed it through separators, smart circuitry, and safer materials, but the risk never vanished. The chemistry was brilliant, not perfect. Still, it became the foundation of the digital age. Every phone call, every drone flight, every electric car relies on billions of ions moving invisibly through layered hosts of carbon and metal oxides. Each battery a self-contained ecosystem, ions as citizens, electrons as messengers, energy as currency. And even as lithium-ion conquered the world, its success seeded the next frontier. Because the more we built, the more we saw its limits. Rare metals, high costs, fragile supply chains, and a world hungry for cleaner, cheaper ways to store power at scale. The question emerged again, the same one Volta faced 2 centuries before. Can we do better? Can we store energy not just for convenience, but for the planet itself? The answer began unexpectedly with salt. Salt, a substance so ordinary it covers our tables and fills our oceans. Yet, hidden in that white crystal is one of nature's most abundant metals, sodium. And sodium, it turns out, behave a lot like lithium's bigger brother. Both metals sit in the same family on the periodic table. Both eagerly give up a single electron to form a positive ion. Both can move through electrolytes and exchange charge in predictable ways. But where lithium is rare, expensive, and mined in fragile ecosystems, sodium is practically endless, waiting in seawater, minerals, and even in our own blood. Scientists began experimenting with sodium-based cells as early as the 1970s. Back then, the focus was on high-temperature sodium, sulfur batteries, powerful, but impractical for everyday use. The molten materials had to be kept near 300 degrees Celsius. Reliable for industrial use, but dangerous for portable devices. For decades, sodium took a back seat to lithium. But as lithium prices climbed and global demand exploded, researchers circled back. If they could tame sodium at room temperature, it could revolutionize energy storage all over again. And they did. In laboratories from Japan to the United States, scientists developed new sodium-ion batteries. They worked almost identically to lithium-ion cells. Same design, same principles, just heavier ions. Inside, sodium ions shuttle back and forth between a cathode made of layered metal oxides and an anode made of hard carbon. Each ion moves through the electrolyte during discharge, while electrons travel through the external circuit, delivering power. When recharged, the ions return home, ready for another cycle. It's the same dance, just with larger dancers. Sodium ions are bulkier than lithium, so they move slower and store less energy per weight. But they bring massive advantages. They're safer, cheaper, and easier to source. For electric grids and renewable storage, where space and weight matter less, sodium-ion batteries could become the workhorse of the sustainable future. Imagine vast banks of sodium cells buffering solar farms, storing daytime sunlight to power cities through the night. No flammable solvents, no rare metals, no global supply choke points. In 2023, the world's first commercial sodium-ion cells rolled off production lines in China. Energy giants like CATL and BYD began designing packs for electric vehicles and stationary storage. The energy world took notice. The age of lithium had met its first true challenger. But even as sodium-ion gathered steam, another revolution was already taking shape, one that didn't just change the chemistry, but the very state of matter inside the battery. For over a century, every battery, from Volta's pile to lithium-ion, had relied on liquid electrolytes. Liquids conduct ions easily, but they leak, they burn, and they limit how densely energy can be packed. What if that liquid could be replaced by something solid? A material that carried ions as swiftly as a liquid, but without the flammability or fragility. That was the dream of solid-state batteries. The concept isn't new. Even Michael Faraday, nearly 200 years ago, discovered certain crystals that allowed ions to pass through. But they were sluggish and brittle, useless for practical power. In the 1960s, engineers developed molten sodium-sulfur cells that used a solid ceramic barrier to separate liquid sodium and sulfur. They were powerful, but required furnace-like heat to operate. The idea of a room-temperature solid-state battery remained a dream. Until the 21st century. Modern materials science changed everything. Researchers discovered families of ceramics and polymers, lithium garnets, sulfides, and oxides, that allowed ions to slip through at near liquid speeds. No flames, no leaks, no explosions. In these batteries, the electrolyte itself becomes the separator, a dense, solid bridge that only ions can cross. The anode can now be pure lithium metal, boosting energy density dramatically. Ions move through the solid like commuters hopping through doorways in a crystalline cityscape. Ordered, silent, unstoppable. Charging becomes faster. Thermal runaway becomes almost impossible. Cycle life extends far beyond today's cells. But the engineering challenges are immense. Every solid electrolyte must make perfect contact with its electrodes. No gaps, no cracks, no weak points. Even microscopic voids can block ion flow and kill the battery. Manufacturing costs are high, and scaling remains slow. Yet progress continues. Toyota, QuantumScape, and Solid Power each race toward the same goal: a reliable, affordable solid-state pack for electric vehicles. Early prototypes promise double the range and half the charge time of today's lithium-ion systems. The first generation could arrive on roads by the late 2020s. The solid-state revolution isn't just about cars. It's about safety, endurance, and energy independence. It's about transforming every device, every grid, and every city that depends on chemical storage. From sodium's humble salt to the crystalline order of solid state, the battery has become a mirror of human progress, from curiosity to control, from danger to design. But there's one more journey left to make, the journey inside the battery itself, where all these forces meet and work in silent harmony. Imagine shrinking yourself down to the size of an atom. Now you're standing inside a battery, inside the heart of what drives the modern world. Around you is no chaos, no thunder, no fire. Just quiet order, ions drifting through an invisible sea, electrons racing through pathways above. Every bit of movement perfectly balanced, every reaction measured in billionths of a second. To your left stretches the anode, the giver of electrons. A landscape of graphite layers or metal structures, built to hold ions between atomic sheets. To your right lies the cathode, a dense cathedral of crystalline oxides waiting to receive them. Between them flows the electrolyte, a narrow corridor of opportunity where only ions are allowed to pass. When a battery powers a device, electrons pour out of the anode, rushing through the external circuit. They light screens, spin motors, drive vehicles, and carry our world forward. Inside, ions migrate through the electrolyte in the opposite direction, ensuring that every charge remains balanced. As you stand here, you'd feel a river of invisible charge flowing past, not turbulent, not chaotic, but steady, like the breath of the planet itself. That's the quiet miracle of electrochemistry. No noise, no flame, no motion visible to the human eye, just potential energy transforming itself into power. Each cycle is a conversation between matter and motion. The battery gives, then takes again and again, like a tide that never truly rests. And within that rhythm lies something ancient, a reflection of balance, of give and take, of energy and rest, not unlike life itself. It's easy to think of electricity as modern, a human creation, a product of machines and metals. But the forces that make a battery work are older than we are. They're the same reactions that shape the stars, the same flow of charge that binds atoms and ignites the sun. We didn't invent electricity. We learned how to hold it still long enough to use it. That's what a battery truly is, captured lightning. A storm condensed into metal and salt, waiting patiently for a command. When Volta stacked his first disks in 1800, he wasn't just building a device. He was giving the world control over nature's current. When Planté made his lead-acid cell, he taught us that energy could be reborn. When Goodenough, Yoshino, and Whittingham tamed lithium, they handed mobility to a billion hands. And today, as scientists perfect sodium and solid-state systems, they're writing the next chapter of that story, a chapter about responsibility, sustainability, and endurance. Step outside at night. Look at the city lights glowing quietly across the horizon. Every lamp, every screen, every heartbeat of machinery is powered by the same principle, a small, controlled transfer of charge. An unbroken chain stretching back more than 2 centuries, from a frog's leg twitching in Italy to the silent cells beneath a modern electric car. The battery has become more than an invention. It's a teacher. It shows us how power can be stored, shared, and renewed. It reminds us that progress isn't about domination, but cooperation between elements, between ideas, between generations. Each advance builds on the last, layer upon layer, just like the very cells inside a battery. Zinc and copper gave us curiosity. Lead and acid gave us endurance. Nickel and cadmium gave us reliability. Lithium gave us freedom. And sodium and solid state may yet give us sustainability. The story of the battery is, in a way, the story of us. Our ability to capture what once seemed uncontrollable, to refine it, improve it, and make it serve life rather than threaten it. From Volta's flickering sparks to the near-silent pulse of today's advanced cells, we've learned that power, when handled with care, doesn't just move machines, it moves civilizations. And somewhere, in the hum of a streetlight or the charge of an EV, the same invisible flow continues, steady, relentless, eternal. A reminder that within the smallest device beats a part of our shared history, the pursuit of energy, balance, and understanding. Because the story of the battery is not just about electrons. It's about human will. The will to improve, to endure, to imagine. To turn what was once lightning from the heavens into light we can hold in our hands. And as the next generation of cells emerges, sodium from the sea, solid state from the lab, we find ourselves once again at the edge of discovery. A reminder that progress never ends, it only changes form. Volta would recognize that spark today. He would see the same quiet wonder that first filled his workshop 2 centuries ago. He would know that what began as curiosity has become civilization's pulse, silent, powerful, and alive. Energy stored, energy released, energy renewed. That is the story of the battery. And through it, the story of how humankind learned to hold lightning in its hands.